Moving on from the loading definition, we will now focus onto the effects of blast loading on the material properties of structural steels, which are affected by the rate of load application. Blast loading results in high strain rates that has the following effects on the properties of structural steels. The yield strength increases to a dynamic yield strength value. The elastic modulus is unaffected by strain rate. The ultimate strength increases to a dynamic ultimate strength value. And finally, the elongation at rupture is very slightly reduced. This is observed here in this graph by plotting the stress-strain response for 5 different strain rates. The above effects are purely material effects and are independent of the structural geometry. The effect of strain rate on material strength can be accounted for using a dynamic increase factor, often abbreviated as DIF. This factor depends on the material type and the strain rate. It also depends on whether the material is in flexure, shear, under axial tension compression. Values for these factors are available from a number of references, and typical values applicable to strain rates for most conventional blast situations are presented in this slide. These values are applied as factors to the static properties to give dynamic material properties. When using analysis methods that can account for strain rate sensitivity in the material model, rate-sensitive material models can be used in lieu of the above factors. One of the most commonly used models is the Cooper-Simmons equation, which gives the enhancement in yield strength due to strain rate as shown in the equation presented in this slide. The constants D and Q provided here in these equations are determined experimentally. We will now move on to the effects of blast loading on the structural response. Understanding the natural frequency, which is the frequency at which the structure vibrates naturally when disturbed, is of vital importance for understanding the response of structures subjected to any dynamic loading, such as blast. A simple example of natural frequency is a tuning fork, which is designed to vibrate at a particular natural frequency. In this graph, T is the natural period, the time it takes for one full cycle to occur. F is the natural frequency in Hertz, defined as 1 over the natural period. Omega is the angular natural frequency, defined as 2 pi times the frequency. The same principle can also be applied to mass springs, beams, and frames. As shown from these graphics, the natural period and frequency of a structure are dependent on the mass and stiffness of the system. Focusing now specifically on the structural response to pulses, we will demonstrate how the natural frequency of a structure governs the response. Particularly, the response can be classified in different regimes by considering only the ratio of the pulse duration to the natural period of the structure. When the ratio is small, and therefore the pulse duration is small compared to the natural period, the response of the structure can be classified as impulsive. The blast wave has completely decayed before the structure has had time to respond significantly. Due to inertial resistance of the structure, most of the deformation occurs after the blast load has passed. The response of the structure in this case is a function of the impulse. When the ratio is large, and therefore the pulse duration is large compared to the natural period, the maximum blast load acts on the structure whilst the structure responds. The response now is a function of the peak overpressure, and the response is classified as quasi-static. Between these two regimes, when the natural period of the structure is similar to the pulse duration, the response is classified as dynamic. So when idealizing the blast load into a simplified pulse shape for the purpose of performing a structural dynamic analysis, we always need to bear in mind the dynamic characteristics of the structure we're analyzing. This table summarizes the importance of each blast parameter in each regime. As discussed previously, the peak overpressure and the impulse dominate the structural response in the quasi-static and impulse regimes respectively.